All right, I think we're in business at the moment. Okay. I'm just going to do a quick audio check here. All right, welcome. As people join, please feel free to post questions in the comment section. Once we have our first question, we'll begin. For anyone who's just joining, we're just waiting for a question to show up in the comments. If you have any particular sections from the practice problems, from web work, or from old exams, feel free to post something there. Hi, Randy, I just saw that. Unit 11, question 36. We can definitely do that. Okay. Let's dive into that. All right. Was there any particular part of this that you had questions about? If not, I'll simply dive in. I just saw another question there from Pendle. We'll get to that one next. So for Unit 11, number 36, the question was to evaluate the integral of e to the x sine of x dx. I'm just going to confirm that's correct. The x sine of x, perfect. So this is, in all honesty, taken directly from the lecture videos as well. So I'm not going to be able to show you anything fundamentally different about how we're approaching this, but sometimes it helps to see it twice. I totally get that. The key thing in terms of thought process is there's no real opportunity here for substitution. That's always the first thing we look for in any integral. And there's no inside functions here. It's just two separate e to the x and sine of x multiplied. So we're going to have to use by parts. And then as we do that, we actually have a choice. The nice thing about it doesn't really matter what our choice is. But I'm going to pick u to be sine x and dv to be e to the x dx. And the reason for that is we have a choice of whether to make the sine function our u or our dv. And I tend to make fewer mistakes when I differentiate sine and cos versus integrating it. I often get the signs backwards. So once you've made that choice, you take the derivative of both sides. Sorry, take the derivative of the u part, and you get du is cos of x dx. And on the other side, you integrate, and the integral of e to the x is simply e to the x again. All right. Then the way I remember the integration by parts formula is just by laying it out consistently each time. Here's our integral. Another way to write our integral is u times v, so sine of x e to the x minus the integral of e to the x times cos of x dx. If there's any comments along the way, please feel free to add them to the feed there. So far, so good. Now, what we notice is that we haven't actually simplified our integral. We've just traded it for a new thing that looks pretty similar to the original, but let's keep going. Let's try doing the same thing again. We keep the trig function with our u and make our dv equal to the e to the x dx again. And just repeat, integral, integral, and derivative. Here we get a negative sine of x, and here we get the e to the x again, and a little mnemonic reminder there about how the pieces come together. And so what we have here is our integral can be rewritten as same as before, so sine of x e to the x minus, and now in brackets, cos x e to the x minus, again, the integral of negative, oops, I forgot a dx here, negative sine of x e to the x dx, close brackets. In terms of Angela's question about does it matter which one that you pick for u and dv, for this particular question, it actually doesn't matter at all. The key thing is that you're going to get back, after two iterations, you're going to get back to where you started. In other questions that don't fit this sine, cos, and exponential, then it may make a difference. Usually the inference is to try it one way and see if you get a simpler integral. The steps don't take that long, and it's usually pretty easy to tell whether you're on the right track simply by looking at the final result of the integration by parts. What new integral did you get? All right, so where were we here? So just tidying this up, we actually have sine of x e to the x minus cos of x e to the x, put brackets here for clarity, and we have a triple negative, so we have minus the integral of sine of x e to the x. The key observation for this particular question is that this looks familiar because that is exactly the integral that we started with. So the integral we started with was, I'll write it in the same form, the sign first. So if we take a look at this integral and this integral are the same if I just move this over to the left-hand side. Because it's negative here, it's going to become a positive on this side. I will have two of them. Now, what does that get you? Well, it tells you that 2 times your integral of sine of x e to the x dx is actually equal to sine x e to the x plus cos x e to the x. Well, that's what I care about. I can just take this 2, divide the whole thing on the right-hand side by 2, and hey, my integral equals this sequence of terms here. So it's a very different way to get to the integral value. We never actually did an integral, did an antiderivative, and got the answer. Instead, we ended up going back in a circle, and by the time we did that, we could then solve for the thing we were interested in. So it just changes the flavor of that. Any follow-ups on that one from anyone? All right, then we'll move on to the next question, which was from the 2016 exam for the distance students. So for those who are main campus students, oops, I'm gonna open the right one here. Your exam was similar, but sometimes the question number shifted a little bit, or there are 1 or 2 questions that are different. We'll take a quick look here. Question 8 for the antiderivative. Oh, there we go. Question 8 for the antiderivative graph. So in this question here, we'll go full screen for a moment. We looked at this at an earlier session, so we'll see if we can do a shortcut for this time around. But I'll just remind you of the connecting factors. So this is the 2016 CDS, or Arts and Science Online, multiple choice number 8. And the graph looks something like this, like so. And the reference points were x2 here and x4. And this is our g of x. And this was the integral of g of x that we're trying to draw. Or sometimes we used a large letter, a capital letter, for those g values. Okay, so then the connection is, how do we go from one to the other? One of the connections, it turns out, is all we actually need for this particular example. The y values on the graph are given, and you can think of this as velocities, and we're trying to draw a position graph, if that helps. But the y values are turned into slopes in the thing we're trying to draw. So what does that mean? That means that the points at 0 especially are interesting to us because those y values turn into 0 slope values. So I should see at x2 a 0 slope. And also at x1, I should see some flat lines at those points. And we can simply check for that on the graphs that we were given. So if I look over here to x2, and I look at the slope there, course, I'm using not the appropriate editor here for this. Second, there we are. If we look at x2 on this graph here, the slope is positive. It's not zero slope, so it can't be A. If I look at B and I look at x2, yeah, the graph flattens out for an instant there. There's zero slope. And if I look down at x4, again, I just look for the slope at that one point, and the slope there is zero as well. So B looks like it's in contention. If we look at C, I see positive slope. The slope is not zero, so it can't be C. And likewise for D, if I look at the slope at x2, it's a negative slope. It's not a zero slope. And because of this graph here, at x2, the y value here is zero. So what I have to see is a zero slope for a tangent line at that location. And the same thing for x4 and x0. So that would be the way to eventually hone in on the answer B for that particular question. All right. Sorry, I just saw your note there, Amy. Yes, grades for, I'm assuming the distance students, but there's some outstanding tests for both questions. For the on-campus students, actually I haven't had a chance to look today even, but the test 3 should be graded by the TAs now and going back out. For the online students, we had some issues with getting stuff to the TAs, for which I profoundly apologize. Test 1 is almost done, and my plan is for a good chunk of this afternoon to be able to spend some time marking test 2. So my goal is to get all 3 tests back to everybody before the exam. In practice, it might be test 1 and test 2 back before the exam, but we'll get everything we can get back to you. So you have the grades and you have the feedback from those tests. I do apologize for the delays, especially for the online students, getting that stuff back to you. That's taken far longer than it should have, for a whole host of reasons. But again, at the end of the day, it needs to get back to you. Yeah, fair enough. I just saw your comment there, Pendle, about the derivative versus antiderivative graph. You would just reverse the process, but you absolutely have to separate the two. Just like when you're going through the integration process, sometimes you switch into doing derivatives for things like the integration by parts. So we're going to ask you to be mentally fluid when going between integrals and derivatives, sort of on a second-by-second basis. All right. Are there any other questions outstanding at the moment? Okay. Angela, I just saw that. Just to confirm, is that the distance exam or is that the on-campus exam that you're referring to? We had some mix-up yesterday and it slowed things down. Okay, so the main campus question, 2017. Here we go. Sorry, section 8, A and B. All right. Just to confirm, Angela, you're talking about the Arctan equation here and the Newton's method? Okay, let's dive in. So this is 2017, main, section 8, section 8. And so here we had an equation with arctan of x equals x minus 0.5. So for something like this, I would be tempted to graph it. You absolutely do not have to, but if you know the graph of the right-hand side, that's just a straight line, intercept minus 0.5. And if you add to it the graph of arctan, which is that sideways tan graph, what you're going to get is an intersection point somewhere in this quadrant over here. And so what we're looking for is that x. So that's nice to know. It's not critical. We can do all the calculations without that, but it just helps give us some ideas. Now, the extra details in the question, we're told that x equals 1, pardon me. We're told that x equals 1 is the closest integer solution, and we're to use Newton's method with this. So the first thing with Newton's method is to remember the process, and the first step of the process is that we need some function of x. The problem with the way the question is laid out right now is we have two functions. We have a function on the left and a function on the right. So to fix that, the easiest way to resolve that issue is simply to shove everything onto the left-hand side. Then we have a function equaling 0. And wherever that function equals 0 is going to be a solution to the equation. All right. So we also need the derivative. We need f prime of x for Newton's method. So for that, we would take the derivative, and we get 1 over x squared plus 1. That's the derivative of arctan. And the derivative of the x is just negative 1. Derivative minus x is negative 1. And the 0.5 is 0. At this stage, we then throw in the Newton's method formula, which has to be memorized. Here's one paraphrasing of it. We have a current x value. We're going to sub that in here into our function and into our derivative. I know the resolution's a little low in the video feed, so I'll try to make that more clear. But we literally calculate the function, calculate the derivative, and perform this combined calculation with all those numbers. I'm just going to go grab a calculator to walk through at least the first step of this. So what we have is x equals 1. However you want to do this, I would do f of 1. Make sure you are in radians because all the calculus that we do with arctan or tan relies on being in radians. We do shift tan of 1, minus 1 plus 0.5, and I get 0.2854. And I think the question said a certain number of digits here, 4 digits after the decimal. Perfect. F prime of 1 is equal to 1 divided by 1 squared. That's just 1 over 2. We get negative 0.5. And so let's call that x naught. The next x value we're going to get is going to be taking all three of these numbers, putting them in this formula. So we're going to get our original x, 1 minus 0.2854 over negative 0.5, and we get 1 point, oops, keep our colors consistent here, 1.5708. That's the process. I'm just going to bring up the solutions here to see or to show how we sort of scale that up going forward. Also make sure I got the right answer there, but I think we did. Perfect. So here's exactly that answer laid out in table form. We ended up with the 1.507. We would do the same calculation. We'd sub that into our function. We'd sub that into our derivative. We get two new values. We'd then go back to our formula, applying the current x minus the two values we just calculated, and get a third value. And that's the process for Newton's method. What we should see is that these values are getting closer and closer to 0, because the goal of our question is to find what x values, so what x values, that's what we're using, are x values, what x values make our function equal 0. And we see that if you repeat the calculations, that at this x value, we get very, very close to 0. And in fact, that leads us to part B. So let's assume that we got to 1.4750, and go to question B, part B. This says determine whether your final approximate solution is close to an exact solution. This is just doing what you would have done back in the day if you were just been asked, hey, does this number satisfy the equation? Well, if we have done some work here, I said x equals 1.4750, that was our third guess, then check with the original equation. If that is a solution, original equation, pardon me, what we should see is the same value on the left-hand side and the right-hand side. So we do the arctan at 1.475. Again, making sure you're in radians. And shift tan 1.475. We get 0.9750. Whereas the right-hand side is our x minus 0.5. This is right from the very top of the page here. And that'll be 1.475 minus 0. Hey, guess what? 0.9750. So these are the same to 4 digits anyway. And that's what we mean by a solution. If I plug the number x into the left and into the right, I get the same value on both sides of the equation. So x equals 1.475 is close to the exact answer. It won't be perfect because we can't solve it exactly, but we certainly have it down to 4 digits of accuracy. Pause there for a moment just to see if there's any follow-up questions. I'm just flicking back to the comments now. All right, I just saw a few things pop up here, so I'm just going to capture them for a second here. All right, so I saw Amy's question for the 2016 section. I have to turn around to do this every time. Sorry, but I'm before that. My screen is just out of my sight line, so I'll do this separately. All right. 2015. Okay, sorry about that. It's theory. All right. So aside from the typos there, those are the questions I currently see in the comment feed. So my proposal is to stay with the 2017 and then work our way backwards to the 2016, then to the 2015. And that way, if people have comments along the way, then we can jump into that same exam rather than jumping around too much. So we'll start with 2017, the main exam first. Then we'll do 2016 and 2015 and do the practice problems towards the end of that. Feel free to just pause the video if those are not your questions. I will try to make it clear when we're starting a question so that you can jump back in just when your question is up. All right, so 2017 main, that's not what I wanted. Right. So this, just first off the bat, is only a question for the main campus students. If you're a distance students, you can ignore this completely. This is 2017 main. In most of the other questions, this doesn't matter, but this one is based on tutorials that only the main campus students had. So for this one, we had a function which was qt plus 1 equals 2qt 1 minus 2qt. So for the stability test for Equilibria here, the idea is always the same. I'm going to translate this into a function of x, where it's 2x 1 minus x over 10. And the idea is that this x or qt graphs against f of x or qt plus 1, we're interested in that graph. And if we ever find an equilibrium point, I think the graph here looks like this. I'm just going to, you only asked about D, so I don't want to belabor the earlier points if we don't have to. Where's the graph? We'll get this right. So wherever we get intersections here, there's going to be an equilibrium. And then our slope test for stability is f prime at, I'm going to call it x star, whatever our equilibrium value is. Equilibrium. If it's between 1 and -1, then the equilibrium is stable. Otherwise, the equilibrium is unstable. And you can show that through cobwebbing or any number of other approaches, but that is that's the process that we use. So then our challenge is to literally calculate the slope at those specific equilibriums that were found in part C. So we need the derivative formula. And you can do this any way you like. I'm just going to differentiate it as is with the little product rule. We're going to have 2 times 1 minus x over 10 plus 2x times over, so I'm going from here down, times minus 1/10, I guess. That's 2 minus 2x over 10 minus another 2x over 10. And just because we're calculating with this, it makes sense to simplify 2x over 5. So that becomes the formula for the slopes of this green graph here at any point. We then just want to find out what those slopes are at the equilibria. Well, we have x equals 0. I should already know the answer to this. First of all, looking at the graph, the slope is larger than 1 because it's steeper than 45. And I also know from cobwebbing that I should be moving away from that point. So I should get a larger than 1 slope, meaning an unstable equilibrium. But just to confirm, f prime of 0 is just 2 minus, oh, that's 2. That's, then we throw in the logic. It's larger than 1. So q x star, whatever you want to call it, q star equals 0 is unstable. And not too surprisingly, when we use our other value, the earlier equilibrium, I'm just going to tab back to the solution so I can grab that without actually calculating it. 5. At x equals 5 or q star equals 5, we're going to get f prime of 5, which is 2 minus 2 times 5 over 5. That turns out to be exactly 0, I think. Yeah. And that's between -1 and 1, so it's a stable equilibrium. Just running out of space here. So that equilibrium we just looked at would be a stable equilibrium. And again, that should match what you found on the cobwebbing diagram done earlier. That tends to be a challenging question in general. Are there any follow-ups on that from anyone? Main campus only, distance students, close your ears, you didn't hear that. It won't be on your exam. Okay, you're welcome. All right, let's do a jump back up here. So we will jump to the 2016 exam. Just gonna make some more pages here. All right, so the 2016 exam, chemistry example in section 9. Let's see if we have that. I assume that's main. Distance. There we go. Right. So for this question, I think it was a different earlier. So this is distance. Distance 9. This was taken straight out of a practice problem. So I'll just make that note at the outset. For reference, this was early in integration, probably a unit 9 or 10 question. But anyway, there's also thorough solutions there, as well as the solutions to the exam. So let's take a look at the actual question itself. So we've got a few different pieces here. There's a reaction that generates oxygen at a rate given by this. So the rate as a function of the catalyst, and it's important to keep in this question all the ingredients clear as possible in your mind. 0.4 plus 0.1 c squared. Is O2 in grams per minute. And again, if there's a particular part of this that you want to look at, just add that in the comments. They're not quite in my sight line, I'm afraid, but I check over my shoulder every once in a while to see if anything's updated there. Speaking of which, I just saw Anshul's question about the cobwebbing. Yeah, I'll go back and do that after we've done this question here. All right. So in this question, then we asked some very step-by-step processes. So let's take a look at the question. Give an expression for the amount of catalyst present during the 5 minutes of the experiment. You're told two things. For 2 minutes, there's no catalyst present. So right away, we can talk about the catalyst as a function of time. And for the first 2 minutes, there is nothing. So that would be our easy start to the amount of catalyst present. After that, she begins to add catalyst at a rate of 0.75 milligrams per minute. Notice nothing about this has to do with rates. There's no oxygen mentioned at all. For part A, we're just trying to get, hey, how much catalyst was there? So if we're adding catalyst of 0.75 milligrams per minute, you can get fancy and do integrals and stuff. But at the end of the day, you also know if I'm moving at a certain speed and I go for a certain time, then speed times time is distance. It's the same thing here. If we do 0.75 times t, and this is in milligrams per minute, and this is in minutes, not I minutes, but minutes, then 2 less than t less than 5. That's going to be basically our catalyst level. So we have 0 for a while, and then C of t, 0 for a while. After 2 minutes, we start adding it, and the slope there is 0.75 until we go up to 5 minutes. Now, there actually is one little gotcha with this, which is if I actually plug in values to this, if I plug in t equals 2, I'm going to get, let's do it this way. If I plug in t equals 2, I'm going to get C of 2 is equal to 0.75 times 2, which is 1.5. Wait a minute. That would be up here somewhere. I would be getting 0 for a bit and then this weird jump vertically. Like, oh, right. I want this line here, but I want it to kind of start or have its origin at time 2 minutes, not at time 0 minutes. That's actually what we would get if we just left it as t. So there's one little fix we would need to make put to that function to make it perfectly match the scenario we're talking about. When t is 2, I'm going to get 2 minus 2 and things are 0. You can think of it as a right shift, but it's essentially bringing to bear the ideas from week 1 of the course. I want to build a graph that has certain properties. How do I build that graph using shifts and transformations? And now when we do that here, we're going to get 0, which is what we want for the concentration. And that is a check mark. There we go. Again, please barge in with questions if you have them or clarification things. All right. The nice easy part is, this is all, sorry, it's mathematically easy. I appreciate in an exam hall when so many things are on the page, it is not straightforward. But if you just go back to the ideas in the question, this is a straightforward question. During the first 2 minutes, well, during the first 2 minutes, there's no catalyst present. We just said that. So part B is the first 2 minutes, which has no catalyst, which means that C is equal to 0, and that means the rate of oxygen production, go right back up to the top here to this formula, is just 0.4 grams of oxygen per minute. Oh, okay, so it's a nice constant rate. Let's take a step back, and we were asked for the rate of oxygen. We're done, that's the answer. Just keep in mind that this 0 value here is the catalyst concentration, not time. That's the hardest thing here, is to keep the different inputs clear. But we're producing oxygen at 0.4 grams every minute. And that makes the answer to part C straightforward as well, because the total oxygen production, well, it's going to be 0.4 grams per minute. Clarify that. Times 2 minutes. And that's going to give us 0.8. When things are constant, they're super easy to figure out how much we're going to generate. So far, so good. I'm going to check in again. Okay. Then the next stage is a little more complicated. This is where we actually have the catalyst changing, but on the plus side, we're just subbing one value into another. So we're trying to find the rate of production. First, this is part D here. We actually had our catalyst amount is 0.75 times T minus 2. And we are literally subbing that into R of C, which is 0.4 plus 0.1 c squared. Well, that's our c right there. So we're going to get 0.4 plus 0.1 times 0.75 t minus 2, close bracket, all squared. So this is capturing, first off, the rate. The more catalyst I have, the bigger the rate is. Now I know exactly how much catalyst I do have at every time point. And so we have all the information combined here. This is going to be at time t, the oxygen production rate in grams per minute. You think, okay, that it's, again, most people overcomplicated this, and a careful reading of the question is essential here. Right, the rate of O2 production, your answer is going to be grams per minute somehow. And the only formula we have that's in grams per minute is our original, going back here, is this original rate equation. So we're just trying to figure out how does this C play a role, because that's the only question mark we had in that function. And last but not least, we'd want to find out the total production, total O2 production. We already found from C that we had 0.8 grams on the first 2 minutes. And we're going to add to that, well, not a huge surprise at this stage in the course, the integral from 2 to 5. I'm going to integrate from 2 to 5 the oxygen concentration formula, oxygen production rate formula, sorry, T minus 2 squared. That is in grams per minute. And we're going to integrate that, multiplying it by little units of time. Well, that's in minutes. Notice we're going from t equals 2 minutes to t equals 5 minutes. That all lines up nicely. And so we have to evaluate that integral. It's not horrible, it's a quadratic. But once we evaluate that integral, it's going to give us a mass in grams of oxygen. We add it to the 0.8 we found for the first 2 minutes, and that sum is the total oxygen production in the whole scenario. Okay, I'm going to pause there for a second. I'm just going to do a catch up on the questions that people were asking about. I saw a few more appear, but if you have any follow-up ones, let me know. All right. All right. We finished that one. And we finished that one. So I think because Angela was asking about the cobwebbing. And I'm just going to see what other ones came in. Addie, I just saw your note. Can you let us know whether you're talking about the main campus or the online exam? They're very similar, but sometimes the question numbers are different. So if you can specify main campus or distance, that would be helpful. Thanks. Great, thanks. Okay, so since we're on the 2016 exam, actually I might get the cobwebbing done that way. I'm going to take a look at the 2016 online section 3 and just roughly the order people came in, and then we'll do the 2015, then PP, and then we'll go back to 2017. So put these in order. Do this one first. We'll probably squeeze this in, but it'll just be a cobwebbing example, not necessarily from 2015. There's 2016 one. There we go. That'll be our new order. All right. Oh, 2016 CDS, section 3. So just to confirm, the LCD panel design is section 3, and that was on both exams. All righty. So a whole pile of details in the question here. The key thing you're looking for here is what you're, it's clearly an optimization problem. It just reeks of that kind of stuff, maybe related rates, but as soon as you see the phrase most profit, then that defines your question. So we're looking for revenue minus costs, and they actually gave you, or sale price minus the manufacturing cost, and they gave us all the values for that. So goal is to maximize P, let's call it profit, capital P, which is the production or the price minus the manufacturing cost. And they give you that for free. And they even give you formulas for each of the ingredients. The cost is 20 times the diagonal length. Actually, the price that you can sell it at is that. And the manufacturing costs are 1 over 576 a squared. So the challenge is we have two variables. We have D's and we have A's, and we can't just differentiate this and set it equal to 0. That's in the back of your mind. What you're hopefully thinking is, I've got a function, I want to find its maximum, I differentiate and set equal to 0. You can only do that if you have one consistent variable. So we have to fix that. And just taking a look at the ingredients here and the picture, we actually have some formulas. The area is x times y. So let's try putting things in terms of x and y. 5, 7, 6, that's x times y. The diagonal would be the square root of x squared plus y squared because it's a hypotenuse. And that's still two variables though. We still have x and y, but we're also told that the ratio of those two ingredients is always going to consistently be 4:3. So it's a 4:3 ratio television set. So if that's the case, then we can turn x into 4/3 of y. That's probably the most straightforward way to do that. And so we can actually write our formula just as a function of y, where it's 4/3 y squared, that's our x squared, and we keep this going, plus y squared, that's the end of our square root sign, and then our x again is 4/3 y's times another y. Okay, sorry, I just saw your note that this was not the question you're asking for. This is the 2016 exam as far as I can tell. I will bring up the solutions in case that's different. Okay, so I don't think it's, anyway, this is the 2016 exam from online. If you can just double check which exam you're referring to, because this should be exactly what's posted. I will check the main campus one and see if it's any different. Okay. So this was the main campus exam, just to be clear about the distinction there. All right, so this is section 3, and this was online. And the question you're referring to is 2016 main, section 3. This problem here. Okay. My apologies for the confusion. It's, again, challenging because we have two minor variations on the course. All All right. So again, it would be helpful. I'm assuming question A probably hopefully wasn't too much of a barrier. I'm gonna look there. Okay. Let's do the whole thing and we'll see where we get. So you've got your formula, which is y equals 5 e to the minus y. That's x. All right. So if we want the y-axis intercept, that occurs when x equals 0. And so we can just slide that into our equation here. And so we're going to have y equals 5, y e to the minus y plus 0. And that doesn't jump out at you as maybe having a solution. But if we're trying to solve anything, the safest way to do it is just by looking for factors. And so we have 5y e to the minus y minus y. And then what we can do is pull out a common factor of y rather, and then 5 e to the minus y minus 1. That to me is probably the most straightforward way to get the roots, because one of the roots comes out of this, y equals 0, and we're done. Or when you have the one of these, this has to equal 0 instead. E to the 5 e to the negative y minus 1 has to equal 0. And fortunately, this is actually one you can solve. 5 e to the negative y equals 1, e to the negative y equals 1/5. You can take a ln of both sides, ln of that, slide a ln in that one, and you get minus y equals ln of 1/5. Y equals negative ln of 1/5. If you're fancy with your log rules, you can actually get ln of 5 out of that, bring the power inside, bring that negative sign as a power inside. And the plus about the fact that we gave you the diagram is you can actually confirm that answer because the solution is around 1.609. And if we go back to the question itself, we had a diagram provided, you can tell that that dot 1.609 is a pretty reasonable guess, pretty reasonable check on the answer that we found. So the answer to part A is y0 and y equals ln of 5 or 1.609. Okay. So part B is where you get into the tangent lines. So we are looking for the equation of the tangent line at the point, and we just found that point. It's x equals 0, y equals ln of 5. So the major thing to do here is to avoid overthinking the question. You want a tangent line? Actually, you want any line, doesn't matter. The two things you need are a slope and a point. Now we already have the point. It's the point 0 ln of 5. So we're good to go for the point. What we need is the slope, and to find the slope, we're going to have to do some calculus, and in particular, we're going to need to do some implicit differentiation, because the slope that we're talking about is dy dx. So I'm just going to make a little bit of room here. Here we go. And do what we did back in Unit 5, and that is to take the x derivative of both sides of this equation. On the left-hand side, the derivative of y with respect to x is dy dx. And then the right-hand side, you have to be a bit careful. You've got a product rule. So derivative of the first times the second plus the first 5y times the derivative of e to the something is e to the same thing again, times the derivative of the exponent. We have the negative, and the derivative of the y would be dy dx, close the brackets. And then the last lonely bit we can't forget is the negative x, its derivative with respect to x is just -1. And so that massive ordeal gives you the equation for the slope dy dx. All right, if that's the case, then what we just need to do is solve for dy dx. We've got a few different terms of it. Pretty much every term actually has something in it. So bring them all to the left-hand side to make sure we don't make any silly sign mistakes. And a plus for this one, plus 5y e to the minus y dy dx. All of that equals -1. And so factoring out every term just has a regular dy dx. So that wasn't transforming anything, that was just factoring out the dy dx. And so dy dx is going to equal -1 over all of that stuff. Oops. Last but not least, we figure out at the point x equals 0, y equals ln of 5, and we're going to get dy dx equals -1 over 1 minus 5, little side calculation here, e to the minus ln of 5 is the same thing as 1 over e to the ln of 5, which is the same thing. E and ln are inverses, so we just get 1/5. So we're going to get 5 times 1/5 plus, need more room here, keep this fraction going, plus 5 ln of 5 times 1 more 1/5. At the end of the day, you get something like -1 over 1 minus 1 plus ln of 5, which actually is just -1 over ln 5, I think. I'm just going to confirm that quickly with the solutions, which are not up yet. Yeah, perfect. -1 over ln 5. So first of all, that matches the picture. We had the graph going like this. We know the slope has to be negative, so that is our slope. And once you have your slope and your point, you put the two ingredients together using any formula you happen to remember for straight lines, but I'll do it this way. The slope is -1 over ln of 5. The point is 0 ln of 5. And so the line is y equals the slope over ln of 5 times x minus x naught, I'll put it in here, 0, plus ln of 5. And this is our slope of m, x minus x naught plus y naught, or f prime of a, x minus a plus f of a. These are all different ways to say exactly the same thing, the way to construct a line based on a slope and a point. And then you can tidy up a little bit with the -0 not really playing a role. And that's, I think, all there is to that. Again, I'm not trying to minimize, but that would be the answer to that question. You have the formula for the tangent line, and you're good to go. Let's pause there for a second for any follow-up questions. Okay, you're welcome. None from anybody else. So let's go, well, we have an opportunity here. We have a cobwebbing question here. This is perfect. And I'm just debating. Yeah, the rules for cobwebbing are actually in the tutorial documents. Let me just do a quick show where that is. Blended. Pardon me as the on-cue websites do their slow thing here. So here we're looking at the on-cue website for the on-campus, and again, distance students don't have to worry about this. Tutorials. Okay. So for this section, the last class that we had, the last activity sheet that we used, looked like this. And where are we here? Sorry, I said that so confidently, and I thought it was in this particular page, but it doesn't seem to be. I was looking for the instructions for the, it has the stability criteria, but I thought it also had the cobwebbing instructions, and it does not seem to. So bear with me for one moment here. I'm just going to open a couple of different versions. Let's do that, and that. There we go. Oh, okay. Okay, now I feel like I'm there. We go. Cobwebbing process. It's on here somewhere. So this is from the group report from the second session. It was mentioned multiple times, but here's where it's actually formalized. Start initial value at the horizontal axis, and then it's repeat this process. Go up and down to the function, left or right, side to side to the y equals x line. That is cobwebbing. And you can see how that is executed here. The blue line is the graph. We started at an initial point that was given to us. We were told start at P naught 0.1. So we start here. This whole scale is 1 out to here. And then we go up to the graph. And then left or right, there's only going to be one choice that makes sense. Here it's right to the y equals x line. Then up or down to the graph, left or right to the y equals x. And it's up to the graph, right to the line, up, and we start seeing a pattern fairly quickly. And that indicates that as we move over time, we're going to end up approaching the equilibrium out here at p equals 1 for this particular example. There is another equilibrium down here at 0, but you notice even though we started close to that, the cobwebbing took us away from that position. So this would be an equilibrium, but it would be an unstable equilibrium. If I start anywhere nearby, I get pushed away from it. I don't know how much more detail you're looking for on that one, so I'm just going to pause for a second and see if there's any follow-up questions about the cobwebbing process. Sorry. I just saw your questions, Addie, and there's two separate ones, I think. Why do we put an x and y value into the slope? Sorry, just going back to your original question there. The short answer is actually we only ever put a y value in, but it's because the formula for the slopes, because it was an implicit derivative, can depend on both x and y, and we are asked for the slope at a specific instance. So this formula is you tell me a y value, I'll tell you what the slope is. I'll do a quick sketch of that graph. So the graph looks like this. If I want to know the slope here, I can calculate it by using the formula that we just looked at, but I need to know the y coordinate where I was. We specifically were asked for the line, and therefore the slope is part of that at this specific point. So we use those specific locations for the calculation. We don't want it in general, we want it at a specific point. Okay, and I'm not sure I understand the follow-up question, the pt plus 1 values. How meta are we talking about this? What are we talking about here? Going back to one of these, this example here. Because in some sense, sorry, the formula is given to you. The very first thing in the question is, here's how you calculate the pt plus 1 values. You take your current population and you plug it into this formula. The result of that calculation is the next population level, or pt plus 1. It's easy to overthink it. It is literally this formula here. If you're struggling with the discrete time thing section, it is almost universally from overthinking it. Every stage as you go through this, there is absolutely nothing new until part D. When you actually do the stability analysis, there's that one last little thing about when is it stable, when is it not stable. Everything else is math that you've seen before. We're just looking at it in a new context. But predicting what's going to happen in the future, well, you have an initial value, so we give that to you. It's as part of the question. And then it's just knowing that what you do to predict to the next time point is take this number and put it into the formula you've been given to get the next time population. And then you do that again. Okay, I know my population now. What's the one after that? Plug it in to the current population and find the next population. You just repeat that over and over to get predictions into the future at adjacent time points, time 1, time 2, time 3, time 4, until you've built up a prediction in the long run. And the graphing for this next segment is the same as any other graphing you would have done. Everything on the right, you think of as your x values, the variable you can think of as your x, and then the remaining part is your y. And you're literally graphing a function, just like you would have. The only challenge is it doesn't look like x and y, so you just have to make that mental leap or that transition if you're struggling with it. That's my 5-cent advice for handling the population models. And then if you look at the practice problems, it's the same thing over and over again. So if there's a step that's not making sense, please do ask, but there are going to be 0 surprises for that question on the exam. Alrighty, so let's do a quick skip back here and take a look. So I think we're back to the 2015 exam is where we're at next. Here we go. All right. So we've done a little bit of this. Oops, that's not what I meant to do at all. For the sake of Pete. Here we go. And that. And that. So yeah, we'll take a look at the 2015 distance section 6B next. Yes. The Arcos one. Okay. Again, this is one that's taken pretty much from the practice problems. So if you're looking for other examples of this, I believe it's the start of Unit 4. Just gonna take a quick peek here. Yeah, there we go. So if you're looking for similar examples, it's also in the notes from the class, end of Unit 3, start of Unit 4. But sine of arc sine, cos of arc cos, tan of arc tan, figuring out what the derivative formula is from first principles for those is all included in that segment there in the solutions to the practice problems. So just as an extra resource for later on. All right, that being said, it is also helpful to see it gone through. So this is 2015 distance section 3. Okay, so find the derivative of Cossacks. That's not too bad. That'll be negative sine of x. Negative sine of x. Part B is you start with cos of arc cos of x equaling x. And we give you the hint to take the derivative of both sides, do an implicit derivative, and see what comes out of that. Okay. Yeah, that's a fair question, Anshul. Do you want to focus on that part, or is that the main question you had about this? Because I think you asked about this originally. Okay, sure. Let's jump to that. So, right, you ended up with derivative of arc cos of x is equal to 1 over sine of arc cos of x, something like that. Yeah, that sounds about right. And then you use the fact that sine squared y is 1 minus cos squared y. And yeah, so here's where you get your square root thing. Plus or minus the square root of 1 minus cos squared y. And so what we did here, oh, sorry, there is a negative sign here already from earlier. So if you do this transformation, we end up with negative 1 over the square root of 1 minus cos of arc cos of x, close bracket, square roots squared. And we claim that this is negative 1 over the square root of 1 minus x squared. And the question you're asking is, why is it not minus here or plus, that kind of thing? So probably the easiest way to answer that is just to look at the graph. So we actually have a graph for arc cos. Cosine starts high, then goes down like so. The arc cosine graph is that reflected, so it actually looks like this is the graph of arc cos of x against x. And so interesting, yeah, there's actually a couple deeper meanings here. But if you look at this graph, at any point, the tangent line, the slope, is always negative. And so we don't change the sign, or we take the positive square root out of this because we already have a negative sign in the scenario. So that's the most straightforward answer. Feel free to ignore everything I'm about to say if you don't want to hear it. That's the answer for this scenario. The interesting thing is we actually had to kludge to get this arc cos function, because cos can't be inverted unless you cut it and just look at one interval of it. If you look at other intervals of the inverse cosine graph, it's basically the cosine graph drawn vertically. In those other intervals, you will get positive slopes. And if you defined arc cos to be this part of the graph, then you would have to have taken the negative square root thing. So depending on where you are in the arc cos graph, you would use plus or minus as appropriate. However, 100, 200 odd years ago, we said, yeah, let's not worry about this other part of the cosine graph. If we're doing the inverse, it's always going to be between 1 and negative 1 this way, and between pi and 0 this way. And if we do that, all we ever want are negative slopes. And so we only grab one root when we're calculating that square root part. That's the long answer for where that comes from. Excellent. I'm glad to hear that, because it's not an entirely obvious thing at all. And I'm pretty sure we skimped over that in the lecture videos. So, all right. Sorry, I'm going to go back here. In fact, we'll probably do Let's take this, copy it down to the end. So, right, so that's 2015, that one. Reason. So yeah, let's take, I apologize for the person who asked about this, but practice problem unit 5, number 34 will be next up. All right, asking the easy ones, love it. All right, so let's do that here. Practice problem, unit 5, number 34. So again, I'm just going to check in because it was someone who was here a while ago. Purusha, I hope I'm pronouncing that roughly right. This was your question. It is a very long question, so I just want to, as much as possible, focus on the part that you found most challenging, I guess, if that's possible. So I'm just going to scroll back down the comments. If you can let me know roughly where the issue was when you were working through the solutions, where things went off the rails, then I'm happy to dive in at that point. In the meantime, I'll start drawing some diagrams, though. All right, so that's the diagram for our scenario. And the key thing is that we are being asked to essentially find a formula for the volume of the water if we're filled up to some depth or height of water, h. Again, just because this is a long question, I'm tempted not to get into it unless the person who asked about it is actually here and listening, because otherwise it sort of falls on deaf ears. So if you asked about this question and can let me know what particular part of the problem was the greatest obstacle for you, then I'm happy to look at that. Otherwise, I'll give it another 30 seconds and then we'll move back to the other questions on the list. Oh, perfect. There you go. I just saw your post. Okay. So again, what was it about this question that was the largest obstacle for you? Based on the solutions, looking through the solutions, where did, it made sense up to here and then things went sideways? Okay, I was afraid of that. All right. All right. So here's the thought process. You're being told some information. Just going back to the question here for a moment. The trough is being filled with water. I hate this browser. The trough is being filled with water at a rate of 0.2 cubic meters per minute. And you're being asked for how fast the water level is rising at a specific time or under a specific condition. So the first step is to translate those statements into mathematical statements. The volume in the trough is increasing at 0.2 cubic meters per minute. Let me just make sure I got that correct. Yes. And our goal, or what we want, is dH/dt. As soon as I have those two ingredients there, what this is saying is we need to relate the volume of water to H. And that is essentially what we're doing here with this shaded in green region on the graph. Our job right now is to come up with a formula that relates the volume to the depth of the water. If we can do that, then I guarantee you the derivative is going to be super easy. We're just going to take the derivative of both sides. That's going to be the easiest part of the problem. The most challenging part is going to be to find the volume. But the nice thing about the volume is that it's volume because it's the same shape going backwards. Let me just do a horrible sketch here. It's the same shape going all the way back, and that is always 10 meters. So the volume is going to be 10 meters, which is our length, times the area in green. And that's going to be two other dimensions. Width and height if you like, but it's not going to be a nice rectangle. Yeah, let's leave it at that. So we got length times area. That'll give us a volume. So the next job is then to dive in deeper on this area. And we can see that the area is going to be different depending on what the height of the water is. So we dive in further into that. Well, we're going to have 10 times. Honestly, I would add it up as 3 ingredients, 1, 2, and 3. In fact, I'm going to label them differently because one of them is easier than the others. Let's label a rectangle 1 and the 2 triangles 2 and 3. The area of the rectangle is, I'm going to change things to meters here. It's 0.3 times H. That's rectangle 1. If you tell me what the height is, I'll be able to tell you that if I have that height and 30 centimeters across, that'll give me an area that I multiply by the 10 length, and that'll cover the volume of water in that part of the trough. And then the next observation is just that we have the area 2, and that's going to be a triangle. And this one does require some thinking. That's why we love rectangles when we can get them. If I think about that triangle, well, we'd probably have to draw it over here somewhere. Let's say that's what it looks like. I'm going to convert everything to meters because that is the units of our volume change was meters cubed per minute. So if we have everything in meters, it makes it easier. And what we have is this big triangle. And then we also have a smaller triangle that is H high. And what I really need to know is this base. Let's call it B here. And I need to know the relationship. Well, fortunately, these are similar triangles. And so what we get out of the similar triangles is that we have 8, let's go B to H, because I really want to know what B is. And that's the 0.25 to the 0.5. And if we solve that out, the base is going to be 1/2 the height. So if we go back to our little triangles up here in green, that triangle, I can find its area as 1/2 base times height. Base times height. And we also have another 1/2 base times height. That's our triangle 3. And then we can use our equation that we just came up with. I'm just going to copy everything down here. In fact, I have 2/2 base times height, so I'm going to just have one. I'll keep it clean. 1/2 already times the base, which is 1/2 H, times the H itself, and then plus another 1/2 times base, which is another 1/2 times H, and another H there. At the end of the day, if we start multiplying all this out, we're going to have 0.3 H's. We'll have a quarter H squared, a quarter H squared. At the end of the day, it'll be 1/2 H squared. That equals the volume of water in our scenario. And that is the major milestone for this question, is just being able to get that relationship between the height or depth of the water and the volume that would then be held in the trough, if that's your volume calculation. Honestly, once you have that, the last part is thankfully much simpler. You have volume equals 10 times 0.3 h plus 1/2 h squared. All we do is take derivatives of both sides, ddt, excuse me, dv dt then is 10 times 0.3 dh dt. And then here we have h squared. That's going to give us 2 h's times the derivative of the inside. That's dh dt. And we know the volume rate of change is 0.2 meters cubed per minute. And we can start solving for dh dt's here. So 0.2 is equal to, both terms have dh dt. So dh dt times 10 times that is 3. And this is half times 2 is 1, so just plus h. So dh dt is 0.2 over 3 plus h. And we were asked for this when the height equals 30 centimeters, which is 0.3 meters. Sub that in for h, and we get 0.2 over 3 plus 0.3, and that gives us a number, which is what the question was asking for. Whew. All right, let me pause there. I need a drink. And let me know if there's any details on that, either this part or the construction of the volume calculation, that still feels totally baffling, and that's totally legit if it does. Okay, I'm glad to hear it. Anybody else have a follow-up on that one? If not, we'll move on to 2017, Main Campus, Section 6. Okay, right. So I just saw your note there, Theo. Yep, we can definitely add 2015 choice and for distance. Okay. Yeah, so we'll do the 2017 one first, and then we'll go back to the 2015. And I mean, please do remind me if there's a question that I've overlooked from anyone, because I think I have the comprehensive list here, but if I've missed one, let me know and I'll add it in. So we'll do the 2017 main 6 first, though. So go back up here. There we go. Sorry, what am I doing here? Did I just say? 2017 main 6B. Okay. Right. So this is also taken directly from a practice problem. I will be forthright about that. Unit 3 or Unit 4, I can't remember, but one of the ones towards the end. It's exactly the same question with literally we changed the 3 and the 4. They were a 2 and a 3 in the original question. So if you're looking for extra practice for these, or where did this come from, it came out of the practice problems. Okay. The single biggest challenge here is interpreting the question, hands down. So we were given one thing, which was temperature change. T is equal to temp change. And we have a formula for that, which is K over 3 minus dosage over 4 times dosage squared. Okay. In part B, we define sensitivity. Sensitivity as S, which is the derivative of this with respect to dosage. And this might feel weird at first, but if you go through the steps, like, okay, how much temperature change do I get for every little change in my dosage? That's exactly what a derivative does. And I'm just going to write this out the way we did in the solution, so it's a little easier to differentiate. So we differentiate this version over here because it's easier. We get 2 over 3 kd minus 3d over 4, 3d squared over 4. And honestly, the hardest thing at this stage is just to remember that's a formula. It came from a derivative, don't care. Don't care in the slightest where this formula came from. The fact is, it defines the sensitivity, and the question in part B is about the sensitivity. All right. In part B, there we go. What dosage level is associated with the maximum sensitivity? Well, how do I find the maximum of any function? I take the function I'm given and I differentiate it and I find critical points, setting the derivative equal to 0. So it doesn't matter that where this came from. I'm just going to take this function, find dsdd, and set it equal to 0 to find critical points. Again, don't overthink it. I have a formula. If I find its derivative and set the derivative equal to 0, I get critical points. So dsdd is going to be 2/3 k minus 6 over 4d. And we just set that equal to 0. Now, the only thing that's a little bit odd is we have lots of constants and variables. D is what we're interested in, is the dosage. So we're going to solve for D. And if we do that, we're going to get 2/3 k equals, turns out to be 3/2 d instead of 6/4. We multiply, we're going to get 4/9 k is d. That is the critical point for the sensitivity. And that's all we're looking for in that question, is just not getting thrown by the definition of this new function, but being able to calculate it. Okay, sensitivity is the derivative of what I started with, fine. And then they ask as a follow-up, what's the maximum value for that function? Well, how do I find maxima, minima? We look for critical points. We take the derivative again for a different reason and set it equal to 0, and we solve, and we get our d value out of that. Okay. I'm just refreshing the page with comments just to make sure I didn't overlook any there. What else have we got? All right, the 2015 distance text. All right. Choice number 10, absolutely. Seems old. Just confirming this one here. This is the Petri dish and cell growth one. Sorry, my Facebook page where I was monitoring the comments is reloading slower than I've ever seen it do that in my entire life. So I'm just giving it a chance to catch back up. Let's look here. Oops. Okay, those are old ones. That's not helpful. Oh my goodness, it's still loading. I apologize. I don't know why it's quite this slow, but again, still loading. My apologies. I'm just trying a different route to get into there now. Okay, sorry, I think I just finally saw the comments coming up here. My apologies for that delay. So, yeah, this is any exponential curve can be assessed or represented by an exponential e base formula. It's just totally up to you how you do it. Sorry, this is distance 2015. Distance multiple choice number 10. And so we're told that we double, pardon me, we're told that we double every 3 hours. Every 3 hours. And start at 6. So the population at 0 is 16, and T for population equal to 8192. That is what the question is asking for there. Okay, so yeah, the bare bones, if nothing else occurs to you with an exponential model, then you can go straight to P of t is P naught e to the kt, and just start using the information provided to solve for k, solve for P naught, everything else. I would hope at this point the P naught as being the initial population and that being given to us, that one's straightforward, or at least familiar. And then what we could do is plug in the doubling. At t equals 3, we're at 2 P naughts. So we'll be at 2 times 16 when we plug in e to the k times 3. That's plugging in our t as 3 hours. When you do that, that lets you solve for k. So you get 2 equals e to the 3k. That gives you ln of 2 equals ln of e to the 3k. The whole point of doing that is your exponential and your logs are inverses, so you get just the exponent down front. And so you get k equals ln of 2 over 3. And then you can go back to your function. So P of t is 16 e to the, I'm just going to call it k still, times t. And we want to know when that equals 8192. The only difference now is that we know this, and what we don't know is what t is. So we can divide through by 16. 8192 divided by 16. Let's try that again. That's better, 512. So e to the kt equals 512. Ln of e to the kt, take ln of both sides. I'm just going to go straight to it. Kt is equal to ln of 512. T is equal to ln of 512 divided by k, but k is ln of 2 over 3. And you just do that long division and you get an answer that hopefully, let's try this, ln of 512 divided by ln of 2 and times 3 at the end of the day exactly 27, which hopefully matches exactly our answer of 27 hours. Yeah. So all the same ingredients, it just turns out to give a different base for the logarithms. And that seems to be the only difference. And for some reason, none of your comments are showing up right now. I can see a bit of a video feed, but that's about it. Again, just give me 1 second. I'm going to try with a different browser. All right, we're loading in. There's comments. Yay. Okay. Okay. So I think we're down to just one, looks like one new outstanding question. Again, if there's one that I've overlooked, please do put it in the comments again. But I see your question there, Pendle. 2016, CDS, and so on. You can absolutely do that. So 2016, distance, section 2C. Section 2C. All right. Okay, right, so evaluating the limit as x goes to 0. So the function is the original one up here, 4x plus a squared over x. Excuse me? All right, so. So I'm just copying down the limit statement. And I guess my question would be, what else could it be? So if x is going to 0, this term is going towards 0. So that's fine. It kind of doesn't play a role anymore. But if we have the denominator approaching 0, we can't just sub in 0. If we get subbing in 0, then things do not exist. Well, that's the same case here. As we get closer and closer to 0, we're dividing by smaller and smaller numbers. That makes the whole thing bigger and bigger and bigger. That shoots off towards infinity. Positive or negative, it turns out it's going to go to positive infinity, but neither one. The fact is it does not approach a number because your denominator is getting closer and closer to 0 while the numerator stays constant. That's really what that would be my argument for how that limit gets evaluated. So we have something finite plus something infinite. That means the finite thing doesn't really play a role. It's going to head towards infinity, or we'd say, as a shorthand for that, excuse me, that the limit does not exist. So leave that for a sec. And then I'll flip over to the second question you asked about. For section 3 for the diagonal. Oh, right. That was the LCD panel design. So the diagonal element for that just came from observing this diagram. There's a right angle triangle hiding here. Excuse me. There's a right angle triangle hiding in here with x and y and d being the 3 sides, and d is the hypotenuse. So somewhere around here, yeah, this would be the expression down here, sort of at the start of this. At the start of this expression here, we would probably have written it in a different way to start with, but at the end of the day, x, y, and d this is a right angle triangle, so x squared plus y squared equals d squared, and we just jump to the square rooted form of that, d equals square root of x squared plus y squared, but it's still Pythagoras either way. All right. I think that's the end of the questions so far. Again, if there's any that I've overlooked, let me know, or if there's anything that you'd still like to look at while we have some time here today, I'd be more than happy to do that as well. Just type something there in the comments. Okay, I'm not seeing any new comments. I'm just going to flip over here and see if that's any different here, but I don't think so. Oops. Here we go. There we go. Okay. That's interesting. I've got a new feed and the other one doesn't show your two new comments there. Anywho, I think we're caught up there. So if there aren't any further questions today, why don't we call it a day? And the last session will run again tomorrow, 12 o'clock to 2 o'clock at the same place. I'll leave it there for the moment. Thank you guys very much for coming out today.